So hello everybody and welcome to another Danish Sound Cluster webinar. My name is Pedro Costa and I'm the host as usual. And today we have a very interesting topic. It is called speaker separation. It is, as the topic says, it's about separating speakers. How do we do that from an audio technology standpoint? We have three very good examples here today to tell us more about that topic in very different angles. And just to tell a little bit about who they are, we have Mads Kvedspool Christensen. Welcome, Mads. Mads is a full professor at Audio and Analysis Lab, CREATE, which is a part of Aalborg University. And then we have Lars Pamslov. He is a senior scientist at Ericsson, also within the hearing world, not only speaker separation, but also different types of hearing technology and research. And then last but not least, we have Rasmus Malik Høyer Lindrup. He's a visiting scholar at ICSI and UC Berkeley. He's also an industrial PhD student at DTU and WS Audiology, and Rasmus also works with speaker separation. So different angles of the same, trying to solve the same issue. So they will tell you much more in detail. I'll let you that to you guys. So the way that this works, we'll have each person talking max 25 minutes, presenting their findings. And then we'll take the Q&A at the very end. So 25 minutes per person, and then the total Q&A at the end of the webinar. You have a section here, which is called Q&A in the bottom. You can press that and write your questions, and we will answer them later. Don't write them in the chat. It's better if you write them directly in the Q&A section. If I forget anything, guys, just fill in because it happens sometimes. But let's start with Mads. So Mads, if you want to share your presentation, go ahead, and then the floor is yours.
Thank you, Pedro. I think I'm sharing my screen now, correct?
You are.
Yeah, good day, everybody. And thanks to the Danish Sound Cluster for giving me the opportunity to talk a bit about our work here. So my talk here today is entitled Speech Separation in Wireless Acoustic Sensor Networks. And first I'll give a bit of an introduction to what this is all about. So we all know this situation from our daily lives with meetings that are being recorded and transmitted elsewhere. And the normal solution to this is some form of microphone array. So a bunch of microphones organized in some known geometry. And in many cases, you could wonder if it wasn't possible to actually better record something like a meeting like that and separate the speech signals if we could make use of all the different devices that we have in such an environment, such as people's phones and laptops and other things you might have in the environment, including the speakerphone we saw before. So in a conventional array, if you compare the two solutions, you have a known geometry. You have everything connected to the same device and with synchronized sampling, and you have centralized processing where you have access to all the signals. On the other hand, in a wireless acoustic sensor network, we have unknown array geometry, we have unsynchronized sampling, and we may have either centralized or distributed processing. And some possible applications of such wireless acoustic sensor networks is, of course, meetings, but also hearing aids that could collaborate with other devices, hearables in general, smart homes, digital assistants, surveillance, and IoT kind of applications. So here's an outline of my talk here. I'm going to start my talk by talking a bit about the multi-channel Wiener filtering, which will serve as the foundation for the separation and enhancement that I'll talk about here. Then I'll talk a bit about speech presence probability estimation. then single channel noise, power spectral density estimation. Then I'll talk about microphone clustering and distributed implementation of all these things, and finally present some results and a summary. Okay, so what is the problem at hand here? Well, from K noisy microphone signals, YK here, we wish to estimate a target speech component SN to improve speech intelligibility or quality, or increase speech recognition performance. So what's difficult about this problem? Well, from a mathematical point of view, you have more unknowns than observations. And then the only way to actually solve this kind of problem is injecting additional prior information into the problem. And that could be about the speech, it could be about the room or noise, something like that, so you can actually solve it. And then I would remark that very often in source separation context, even defining something like the target speech is difficult. And certainly in a sensor network where you don't even know where the different microphones are, it's even more difficult. But let's see if we can do something about that. Okay, so at microphone K here, we observe a noisy speech signal, and SN is what we call the clean speech at microphone 1. And GK is the impulse response from the source to microphone 1, and EK is the noise, which I'm using the term noise broadly here to include not just diffusive and stochastic noise sources, but also interference speech. And then we will absorb the impulse response for the different channels with the speech, such that we have an XK, which is the clean speech signal recorded at microphone K. If you then try to look at this problem in the frequency domain with the additive noise and the impulse responses there, then we can see here at the bottom here that we can describe it as the multiplication of an acoustic transfer function with the speech, and then we have the additive noise there. So we also have the additive noise model in the frequency domain. And we can, of course, collect all the K microphone signals in a vector such that we have it nice and complexly written like this. So we have our observed signals for the different microphones here. For frequency omega here, we have the different acoustic transfer functions, TK, which are just scalar quantities that are multiplied onto the S here, which is a scalar quantity here. And then we have different noise signals here. So let's say we apply a filter then to extract from Y an estimate of the speech. So we would like ideally that this filter H filters out E, E, the noise term, and doesn't change S, or if it does, we know how much, and it only does so minimally. So, and you can of course see here that written applied to the model result number 4. We have a term here involving the speech and a term involving noise. This we would like to get rid of, and this one we would like to preserve S as best possible. And of course, these two things are very often mutually exclusive. Yeah. So if we define the objective and mean square error, that we want to minimize the difference, the expected value of the squared difference between the target speech here and the output of the filter as applied to the speech part, and minimize the noise power here. Then the minimizer of that combination there is the multi-channel Wiener filter, and it has this well-known kind of solution that you see here, where we have the inverse of the observed signal covariance matrix here, and the first column of the same of the matrix there, and then we have phi EE, which is the cross power spectral densities of the noise signals that we see here. So so we have these two quantities that we need to know to compute this. And of course, the observed signal here, we can easily compute here, but then what's more difficult is how we find the noise statistics. Okay, so looking at the problem this way is nice in the sense that we do not actually need to know the array geometry, so or thinking of it in terms of G's to implement the multi-channel Wiener filter. And this multi-channel Wiener filter can actually cope with unsynchronized microphones to the extent that this G here will absorb the synchronization errors. So for example, clock offsets. And it's also nice that there's extensive literature on how to implement the multi-channel Wiener filter in a distributed way. So that's also very useful. And as I said, the signal covariance matrix is easy to compute, but the noise statistics is of course much harder, and that's what we're going to talk more about. And the key to solving that problem is something called speech presence probability. So we talk about how to estimate that. So if you look at two microphones, I and J in frame L, the noise cross power spectral density by hat E, I, E, J here at frequency omega and L here can be recursively estimated in this fashion that we see here, where we have this alpha here and 1 minus alpha over here. And then this alpha is what we call the speech presence probability here. And then what you can see here is that when this alpha is high, so close to 1, this is between 0 and 1, we will take the previous estimate of the noise statistics that we have there. Whereas if alpha is low, what we will do is actually we will update the statistics with the observed signal statistics. So in traditional voice activity detectors of VATs, we make a hard decision where we have two hypotheses, where H0 is the one where there's no speech. And in that case, we set this alpha equal to 0. And we update our noise statistic from the observed signal. There's no speech, since there's no speech. And in case there is speech, we set alpha equal to 1. And then we simply use the last one. So that's a very simple principle that we use here in the VAT. But SPP here is actually a soft decision where this alpha is, in fact, the posterior probability of the first hypothesis, H1, for a particular frequency and in a particular segment here, given the observations and model parameters here. Yeah. And so the question is, how do we compute this SPP? Because if we have that, we can actually sample the statistics at the right time and the right places in the spectrum where we know there's actually noise with a high probability. This work, I should say, by the way, was published a few years ago in JASA, in case you're interested in the details. Okay, so for microphone K, our signal model is that there can be two cases. There's no speech, we call it H0 here. And in that case, our observed, the likelihood function here, which is the parameters of that is the noise. And here it's the noise statistics here. And this is a complex normal distribution with zero mean and variance phi EK here. And in case there is speech, then we have two parameters, namely the variance of the noise and the variance of the speech. So this is a very simple model for a particular microphone, just making use of the variance of the noise and variance of the speech here. And this model right here is not completely consistent with duration of multi-channel Wiener filter because it ignores correlation between the microphones, but it is something that can actually work because it enables us to estimate those same correlations for use in the Wiener filter. And the model parameters are then, so this phi K here for the K microphone here, and the frequency omega and segment L is simply these two variances here, the noise variance and the speech variance. And based on this model here, we can calculate the likelihood ratio here, L, as the ratio between the two posterior probabilities here for the two hypotheses. And we can express that using this well-known expression here involving what is known as the a priori SNR in the speech enhancement literature. So that's the ratio between the speech variance and the noise variance here. And you can see other than that, the expression involves the squared value of the spectrum of the observed signal evaluated at the frequency we're looking at here. Yes. Okay, then combining these likelihoods across channels here and assuming independence here, we can simply multiply these likelihoods here, as you can see in these the posterior probabilities and the likelihoods here and we can obtain the SPP, as you see down here, the alpha, which again was the posterior probability of hypothesis 1, given the observed signal and the parameters here, in terms of the priors of the two hypotheses there and the likelihood ratio we had here, the one here, as you see there. Yeah. Yes, and one thing I should note here is that we can easily incorporate multiple frames and multiple frequencies in the computation of the likelihood ratio here. So all that, we can incorporate more information if we want to, and we can study the effect of doing that and see if that helps us solve our problem. Okay, so what did we observe? If we have the SPP, we can estimate the required noise cross-power spectral densities to run the multi-channel Wiener filter. And this SPP can be computed as the likelihood ratio for every channel, and then a combination of the k likelihood channels with prior probabilities. And to compute the likelihood ratio in channel k, we need to know the parameters theta here, which were the noise variance for a particular segment and frequency, and the same thing for the speech. Now, these two quantities are, of course, unknown in practice, and we must estimate them somehow to do that. And that's what we're going to talk about next. So many methods now exist for single-channel noise power spectral density estimation, and perhaps the most well-known ones are minimum statistics dating back 25 years, the IMCRA method and the MMSE methods, all of them well-tested and well-known to anybody working on these problems here. The thing about these methods is that they work really well for stationary noise, and they're very simple, but you can also very easily see that they perform quite poorly for non-stationary noise. So in some of our previous work, we developed a model-based noise power spectral density estimator, which works much better for non-stationary noise. And for example, we looked at Babel noise. So let's take a look at that. So recall that we modeled the kth microphone signal here as this complex Gaussian distribution here, where the variance of the distribution is given by the variance of the noise plus the variance of the speech here. So what we do to estimate these two quantities here, which are essentially just power spectral densities, is that we assume that the clean speech and noise can be accurately modeled by autoregressive AR processes. And then we pre-train code books or dictionaries, whatever you want to call it, of these AR parameters here such that we get a model that represents typical speech and noise. And then we form models of the microphone signals from all combination of trained speech and noise power spectral densities. So we do this for each microphone signal, and then we infer model parameters and probabilities and compute model average power spectral density estimates. And this all takes place for each individual microphone. So a bit about the autoregressive spectral modeling, which is of course an old model in speech processing. A nice thing about it here is that it's really low dimensional. Yeah, so the power spectral density of an AR process is given by this expression here. We see here of numerator, we have the variance, which scales the power, and then the model itself is parameterized by the AR parameters AP down here. So we can think of this as a scaled power spectral density here, phi tilde AR of omega that you see here. So what do we have here? Well, we have an excitation variance, we have the AR parameters, and we have this normalized spectrum here. And then generally also for a low AR order and a stable AR, we have that this spectrum is smooth. So the idea in training the AR cookbooks is that we can take clean speech and noise in isolation, and we can train models of each of these. And this is something that Srinivasan looked at in 2006 and 2007. And you can be as specific and general as you want with these codebooks. You can train speaker-specific codebooks if you want, and you can have codebooks that are quite general or quite specific depending on what kind of acoustic scenarios you're dealing with. Yeah, so a model ML, as we call it here, is formed from a combination of AR vectors in the speech and noise codebooks. So this likelihood here for model ML here is given by a complex normal distribution, again, zero mean, but then these scaled spectra here. And then the only unknowns in these models here is actually these scalings of the different models that we have here. And then to infer the model parameters and computing the involved probabilities, then for every model, the excitation variances, sigma squared xk and sigma squared ek, as well as the model probabilities, can be computed using a variational Bayesian algorithm. And this actually also produces the power spectral density estimates of the speech and the noise for every model, for every microphone. And then final PSD estimates are for each microphone are obtained, like you see here, with all these different candidate models here, weighted by the different posterior probabilities of the different models here and added up. But the end result is just that for each microphone, we have actually a model of the two spectra, the speech and the noise. So what do we see here? So to estimate the single channel power spectral densities, we used autoregressive models trained on typical speech and noise data. And this approach is advantageous because it reduces the number of unknowns to just 2 model parameters in every frame, which was the excitation variances. And it allows us to include prior information about typical speech and noise signals and even specific ones, as I mentioned. And we computed the PSD estimates from model averaging. And the conclusion from this is actually now we have the information required to run our multi-channel Wiener filter, because now we can actually sample the statistics in our network of microphones to perform the filtering. So, but before we move on to that, so in principle, we could do that right now. But before that, let's talk about another idea here. So recall that we have for each microphone K, a speech and a noise model parameterized by A parameters. And then the idea here is that what if we use the single channel models for clustering of the microphones? Then each cluster would contain mics observing the same speech and noise spectra. In other words, if in a meeting scenario like we saw earlier, we would expect that microphones near a particular speaker would tend to cluster together. So having formed such a cluster, we can then take the signals from those clusters and perform enhancement of the closest speaker using a subnetwork of the entire network. So how are we going to do that? Well, what we propose is to use the Ichikawa-Saito divergence between two spectra. So we have an observed spectra phi and then a model phi hat that we want to measure the distance between these two spectra here. And then this is given by the expression that we've seen here, and this has been used extensively in speech and audio processing for many, many years. So it's the integral over the entire spectrum of the ratio between the two spectra minus the logarithm to the ratio between the two spectra here. And in our case, for each mic K, we had that the speech and noise models were given by these two expressions here. We had all the candidate models weighted by their posterior probabilities like that, and then added up. And the idea then is to assign mics to clusters using the following divergence between the centroid of a cluster C and a microphone K, as you can see down here. So measuring individually the Ichikawa size distance between the potential cluster centroids here, the muse, and the speech, and the same thing for the centroid for the noise and the noise models there. And then the cluster C index set here is defined as the one that produces the smallest Ichikawa-Saito. And the centroid for the cluster is given by the mean of all the power spectral density estimates of all the members of the cluster here. And actually, this centroid here, in case you're wondering, is that optimal for the Ichikawa-Saito? And yes, actually, you can show that it is. And then you do the same thing. This is for the speech, and you can do the same thing for the noise here. So in essence, the microphones are assigned to the cluster that has the closest centroid in the sense of the IS divergence. And then the centroid is simply the mean of the members of the cluster. And this clustering, in case you're wondering about sort of real-time applications of this, it's not something you need to do all the time. It's not something that needs to be updated faster than the acoustic environment changes. So you can do that on a completely different time scale that you would perform the actual enhancement. Yeah, so the computations that are involved in doing all this is finding optimal speech and noise models for microphone K. That's a local computation. Performing a clustering based on these models, that's a global computation, and then computing the speech presence probability, which is also a global computation. The global computation problems can actually be solved using distributed consensus averaging methods. And the one we used in our work is the asynchronous PDMM methods, which can solve these problems efficiently. All right, let's take a look at some results here. And these are the results from the paper I mentioned before. Yeah, and the results will focus on clustering nodes near speakers using distributed k-means with order estimation, computing the speech presence probability for each cluster, and the algorithms for distributed processing here. And I should mention here that the results in this paper here perform the clustering slightly different than what I mentioned here, but I don't think it matters too much. Okay, so this is in a simulated 10 by 10 by 3 room with a T60 of 200 milliseconds. And we use 50 random placed mix with connections to other mix within 2.5 meters. So simulating that the microphones will only be connected to ones in its proximity. And here we use 3 speakers with the same power as an example. And then speech models are trained on Timid and noise is trained on Aurora, and testing is then done on a different noise set, namely noise X92. Okay, so here's a picture of the room or the plane in the room, the floor plane, and then all the blue dots here are the different microphones. We call them nodes in graph theory, of course. And then the nodes that are connected are the ones that have shown to have connected here. And then we have 3 speakers. We have speaker 1 over here, speaker 2 down here, and speaker 3 over here. And you can see we have lots of microphones in the vicinity of each of these. So here's an example of what happens if we perform this clustering with background noise being babble noise at an SNR of 10 dB. You see we get a cluster down here near one speaker and the red one up here, and then the blue one up here with the first speaker here. So you see that actually the microphones nicely organize themselves into subnetworks like this. Here's an example of the SPP estimates here. So the ground truth is one up here, and then the estimates are the estimated ones are the ones that you see down here. You can see that it does a fairly well job here. And this is for a false alarm rate of 0.2 in this case. Yeah, so here's the ROC curve, false alarm versus detection rate here. And you can see that if you just use the clustered node, you get the red curve, whereas if you're using all the nodes, you're getting the black one here. So you can see actually you get better performance actually by using only a part of the network, subnetwork here, which confirms that this is a good idea. And so this was for speaker 1. If we then go to speaker 2, again, we can see the same story here, that we get better performance just using the second one. And yes, and here we see the results for speaker 1 and babble noise at an SNR of 10 dB here, as compared to the minimum statistics method, the black one, and the MMC method here. And you can see you actually get much better performance with the model-based approach here, which is much better at handling babble noise. Yeah, and here you see how the whole picture changes as a function of the number of iterations taken by the network in computing the speech present probabilities and forming the models and all that. So if we use centralized processing where we use all microphone signals, we get the red curve here. After 5 iterations, the network has achieved the performance of the black curve here. And then we can see if we do 10 iterations, we get closer to the red curve, as you can see here. So you can see we get better and better performance the more iterations we run there. Yeah. Very good. So what have we seen here? Well, we have seen that we can perform speech enhancement and speech separation using the multi-channel Wiener filter for wireless acoustic sensor networks. But to do this in this framework, we need to know the cross power spectral densities to run the Wiener filter. And we have used the speech presence probability concept to estimate the noise cross power spectral densities from the single channel noise power spectral densities. And we have shown how the single channel noise power spectral densities can be estimated using a model-based approach, and that we can cluster the microphones using these models here. And on top of that, simulations show that the clustering of the microphones actually increases performance, and also show that we can, in a few iterations, implement these things in a distributed and efficient fashion here. And I also want to add that now this way the core idea here of clustering microphones and sampling statistics of that also applies, of course, for other models capable of estimating SPPs, for example. So it's entirely possible, of course, that you could obtain even better results with for example, some of the deep learning based methods as an engine for computing some of those things there. But what we have here is something that is simple and very, very operational and could form the foundation for enhancement and speech separation in a wireless acoustic sensor network. Thank you.
Awesome. Really good. I'm glad you could see a good result in the end. So if you could stop sharing the screen, then Lars can share his screen and start soon. So we'll take the Q&A afterwards. We already have a few questions, but Lars, can you stop sharing your screen? Mats? Can you guys hear me? Lars, can you unmute, please?
Yes, and do you see my screen now?
Yeah, now I do. Okay, cool.
Now you do, okay.
All right, so
okay.
Just go ahead.
Well, now for part 2. So my name is Lars Bramslev. I'm a principal scientist at the Ericsson Research Center, which is part of Oticon, the hearing aid manufacturer. And I'm presenting this work together with collaborators from Tampere University of Technology. That's Gaurav Naitani and Tuomas Virtanen. And this work is about separating speakers for hearing impaired listeners, and there is also a bit of noise reduction in here. So here we go. Just a moment. So first, I'll give you the application for the speaker separation, where we have 2 competing voices that we're separating. That turns out to be a somewhat easy problem. And then the noise reduction, which is a more common voice and noise scenario, and that turns out to be actually a more challenging problem. And then you will get the summary after that. So for the speaker separation, what if you can imagine we have this sieve, and sorry for my voice, I have a bit of a cold today. You had this sieve that could actually separate 2 voices through deep neural networks and present one estimated voice to one ear and another estimated voice to the other ear. That's the basic idea in this project. So we have an algorithm that can separate the voices with low latency, and that's important to highlight. It's only an 8 millisecond delay, and the latency is a very important parameter in hearing aids. As soon as you have open fittings, it's important to keep the latency very low. Excuse me. The way it works is that we take the mixture of the 2 voices, extract what is really a spectrogram, and then we use the deep neural network to, we feed the spectrogram to the deep neural network, and that estimates a mask, which is really a ratio mask. It's shown here by the sieve and the inverted sieve. And that means that each bin in the mixture spectrogram is either assigned to source 1 or is assigned to source 2, and then it's inverse transformed back into the time domain. And we do that in a traditional way by training the deep neural network with the true signals. So we are feeding the clean signals, the 2 voices, back into the model, and we are training it using back propagation, just as you normally train a deep neural network. And in this case, we have 3 minutes of clean speech available. So that's all it takes to train the model, which also means if you were to train this in the real life, 3 minutes of samples of a known voice would be enough to train such a system. For instance, your spouse or what it would be. If we look at the mask, the ratio mask, so what you see here is a spectrogram of the mask. In this case, it's an example where we separate speaker F2 from a mixture of F2 and F3. So the upper half is the ideal ratio mask. So that's when we know it's basically computing the ratio between the 2 signals, the 2 voices. And what you can see then is once we've trained the system, we can estimate a mask. That's what you see at the bottom. And they are not exactly the same, as you can see. But you will also hear that that's actually good enough. Let me show you an example here. We have 2 sentences played on top of each other. There are 2 sentences from the Danish hearing and noise test. The sentences you hear are not necessarily the same as you see in the text, but it's just to indicate what we do. And these voices were known for the training. So here's the mixture.
Min kuglepen skriver med rødt.
And I hope you could hear that. Pedro is nodding. Okay, so here's the mixture again. Let me do it once more.
Min kuglepen skriver med rødt.
Right on top of each other, two male voices. Here is one voice extracted from the mixture.
Posen her er til grøntsager.
You can hear the other voice faintly in the background, but it's doing a very good job.
Posen her er til grøntsager.
And then the other male here.
Derhjemme spiser vi ikke kød.
So you can only hear the voice that is suppressed is very weakly there. So it's doing quite well.
Min kuglepen skriver med rødt. Posen her er til grøntsager. Derhjemme.
On to the next slide, just a moment. So the Danish hint material, as some of you might know, consists of 13 lists of 20 sentences each, and that's what we use for the training. We have 3 males and 3 females in an enlarged version of the corpus that we created ourselves. And we combine them in male-male, female-female, and male-female pairs. And then we train the system in a speaker-specific way, so for a particular mixture. But there isn't a whole lot of lists to use from. So what we do here is we use 4 of the 13 lists for the training, 1 for the validation during the training, and that leaves us that leaves us 8 for the listening test. It's important you always test on different material than what you trained on. So we ran this competing voices test in 2 different ways. In the first situation, we queued by, let me see if I can give you a pointer here. Yeah, there should be a pointer. In the first situation, we queued by the first word. We call that a single target, because then you know at the beginning of the presentation which one of the 2 sentences is actually the target sentence, and you know what to attend to. So that's an easier scenario. Again, so you would either see derhjemme or you would see stay tuned on a screen. If we queue by the last word, that's where it gets difficult, because you have to maintain attention to the 2 sentences at the same time. So you would hear the entire mixture here, and then it would say either kød or hoved on the screen after you've heard the mixture. So that's a much more challenging task. And when we ran the listening test, we just applied linear gain to compensate for the individual hearing loss. Yes, and we ran the test on 15 hearing impaired listeners with an audiogram looking like what you see to the right. The picture to the left is just somebody that is not harmed by GDPR. So that's why I used that. We had 5 processing conditions. So first, of course, is the unprocessed mixture that you just heard. Then we had second, we have the ideal. So that's just the separate. That's equivalent to the ideal ratio mask that I showed you before. So that's the best you can ever get with such an algorithm. That would be the performance for the separate condition. And then 3 different types of deep neural networks: feed-forward, a traditional feed-forward deep neural network, a long-term, short-term memory model, which has some memory built in, and also a convolutional recurrent neural network, which also has memory built into it. And all of them have roughly 3.5 million weights. So it's still at the stage where it's a lot to fit into a hearing aid. And let's have a look at the results. So for the competing voices, you can see the results here in the word score. The word score is just the number of correct words repeated in the hint sentences, and the sum is right above 50%. And the separate, which would be the ideal, is around 75. And then you see the 3 deep neural network conditions somewhere in between. This is the case where they have one output to one ear and another output to the other ear. So they can choose to attend to whichever one they want to. And I should also say that we ran a few tests like this on normal hearing listeners, and they can do almost 100% for the sum condition. So it's an example of something that's easy to do for normal hearing listeners and quite difficult to do when you have a hearing loss. And if we look at the middle one, the LSTM seems to be the best one, although there is no statistically significant difference between the three of these. But the LSTM has a 13 percentage point increase in the word score. So that's definitely worthwhile. And that is significantly different from the sum condition. If we then take another example where we just choose one output, that would be the same as the user could on a smartphone select one or the other. Or if it was controlled by eye gaze or something, it would depend on the direction you were looking. And there you can see that you have almost perfect results. Of course, the separate is perfect because there's only one signal to attend to. But even the three DNN conditions here are doing very, very well. And this gives us the 37 percentage point increase in the word score. So that's very, very nice. The other thing I should mention is if we look at the individuals in the test, I mentioned we had 15 test persons, and the base performance for these is very, very different. So for the sum signal, you can see the circles here indicating that some have very poor scores for the sum conditions, and others like here have very good scores. And it's very logical that if you have very good performance, you don't really need a system like this. So there's little room for improvement. But if you have very poor performance, like some of these over to the right, there's a big room for improvement, and you can get really high benefits for the user. Okay, so let's get on to the noise reduction then. The voice and noise is, you could say, a slightly more common scenario that's often encountered. And this is where we want to see how does a similar system similar to what you just saw, how does it perform when you do the noise reduction instead? And we also, in this test, looked at the generalization ability. So what is the effect of enhancing an unknown voice rather than a known voice, as we did before? And furthermore, we had some new deep neural network and some new candidates for the mask that we estimate. So it was a progression from the first test. Here we had 7 conditions. In this case, number 1 is the sum. So that's just the mixture, the input to the system. And number 7 is the ideal ratio mask. So that's what we can do when we cheat and know the signals. And then you have different types, either the feed-forward network or the LSTM network, with respectively known and unknown voices, and then some more fancy ways of estimating the mask that I won't go into details with now. We had maximum 20 dB of attenuation, so we don't have infinitely down to 0 attenuation, which would be minus infinite. We don't do that because that turns out to have a worse sound quality, and if we could just get 20 dB, that would be a dream come true anyways in terms of the speech intelligibility. And again, we have weights, we have networks that have around 3.5 million weights. So here the corpus was similar to what you heard before, the sentence corpus, but now we had 6 males and 6 females, so 12 talkers all in all. And we had between 200 and 260 sentences for each talker. That's equivalent to 6 minutes of speech roughly per talker. We had 4 target talkers that we tested for, male 1, male 2, female 1, and female 3. And when you do it speaker dependent, you train on these particular target talkers, but in such a way that you never train and test the same sentences, you test on different sentences. And in the speaker independent situation, we don't train on the target talkers, but on all the other talkers. And then in this case, the noise was either a party noise, so somewhat modulated, like a multi-talker babble. And we trained at from -3 to +3, rowing that signal to noise ratio, and we tested at 0 dB signal to noise ratio. And the other noise was a shopping center noise, which tends to be more low frequency and more stationary. Again, trained at -3 to +3 dB and tested at 0. Let me give you some examples of this. So you can see here now there's only one target sentence, and it's on the background of noise. So we can take the mail in the party noise. Let me see. I have to remove my laser. Just a moment. The mail in the party noise. It sounds like this. It's not easy. We're talking 0 dB signal to noise ratio. Here's an example of the mail extracted from that party noise. You can get it one more time. And you can hear there are some artifacts and some things that get cut out, some consonants in particular. And the mail in the shopping center is here. That's somewhat easier to understand, at least the mixture there. Still 0 dB, and then the mail extracted. You can also hear that there is something that's not so good. There's parts of the sentence that are missing. So let's take a look at the results. Beautiful. Here are the results. So again, number 1 here is the inputs, the unprocessed mixture, and number 7 is the perfect. And again, you can see at number 7, the ideal ratio mask has very high scores. Don't be confused by the fact that they're above 100. That's because they have been transformed to this Rao scale, which actually extends beyond 100. So they're quite good. And the mixture again is at around 50%, somewhat lower for the party noise than for the shopping center noise. And only some of these actually turn out to be different from one another. And that's for the party noise. We get a 16 percentage point increase for the processing 2 condition. So that's the feed-forward network with a known voice. And interestingly enough, we get the same benefit for the processing 4 conditions. That's actually the LSTM network with unknown voice. So that's a bit peculiar that the unknown voice is doing better than the known voice. Perhaps because we have more training material. When you do unknown, you can train on all the other voices, and that gives you more training material. Yeah, so that's also a worthwhile benefit, I would say, corresponding roughly to 1.5 dB or so. So conclusion for the speaker separation is that we get a relevant significant effect of 13 percentage point. That was the first study I mentioned. The user here has all the information, so they can attend to whichever voice they want to. And if we choose to leave one out, that's what I call the target masker test. There is the target and the known target, and there's a masker. We get a very large effect of 37 percentage point. And this is a case where the user must choose, leaving out the other talker completely in the scenario. And in this case, all the DNN modes give us the same improvement. So really the simple straight feed-forward network is just as good. And there's a reference there at JASA 2018 where you can read more about it. For the noise reduction, we get a 16 percentage point benefit improvement in the word score, roughly equivalent to 1.5 dB. That we get that for the known voice feed-forward network and for the unknown voice long-term, short-term memory network. And then the shopping center, there's no benefit. And the reason for this, I believe, is that there's just less glimpsing opportunities. So you have a very steady noise, and then there's little glimpsing opportunities that the network can exploit to highlight one or the other. If you take the first examples with the speaker separation, where you have 2 clean voices but no background noise, that means there's lots of opportunity for glimpsing, where one places in the spectrogram where one voice dominates over the other. And I would say unknown noise is still a challenge. It was not something we've tested, but in this case, in these examples you saw, the noise was known. And that's making the job easier, because once you have unknown noise, it's harder. And of course, there are infinitely many noises that the user is exposed to. So that's the end of my talk. Thanks for your attention.
Thanks, Lars. That was good. Do you have an idea why the glimpsing occurs, or is it a complete black box because of neural networks? Or
well, we sort of did a little investigation into the weights in the network, but I must say we didn't come up with any clear answer. So it is a bit of a black box.
Mm-hmm.
And you can say from a research point of view, that's a disadvantage, but the performance of these systems is just so much better than the older, more traditional algorithms that have been applied to the problem.
Cool.
Like the k-means clustering.
Like the what?
Like the k-means clustering, which is an older traditional algorithm.
Right. All right, cool. We'll take your questions later. I don't have many, but if you can stop sharing, then Rasmus can start his presentation. Thank you. And unmute whenever you like. Lars, if you have to go, it's also okay. You decide.
Okay, I'll see how it goes.
Okay, cool.
Fantastic. Thank you, and thanks for the opportunity here. So yeah, my name is Rasmus, and today I'll talk a little bit about some work we've done on trying to see whether we can improve existing deep learning approaches to speaker separation by doing variational inference. I'll try to walk you through a thing that we call probabilistic representation learning, what that is, and I'll try to connect that with speaker separation and how we can improve the generalization that Lars also touches upon. And Mads also talked a little bit about variational inference. So that's a core concept of what we're doing, and it ties into all of this before we wrap up. I'm an industrial PhD. I'm with WS Audiology, and my project is also partially funded by the Innovation Fund Denmark, but I'm at on the university side of things, I'm with the section for cognitive systems and the hearing systems group out at DTU. But yeah, jumping into it. Probabilistic representation learning. Starting out with what I think a representation is. If you were to solve a problem of either, say, speaker separation or speaker identification, to keep it a little bit simple, a traditional pipeline might look a little bit like this. You have an audio waveform on the left-hand side, and that goes into some system, and you want to predict, say, a speaker identity. And traditionally, you might have a feature extractor, say something that produces middle frequency catch-term coefficients or something like that. Could also, so far we've been talking a lot about spectrograms or spectral representations. That could basically be this yellow box. It produces some sort of condensed informational representation that is easy to work with in some sense. And that's what I think of as a representation. You might think of it as a feature too. And then this is a feature or representation extractor. This sort of condensed informational nugget is fed to something else. It could either be the classifier that Lars talked about with trying to identify time frequency components that should be masked or not masked, or it could be a simple classifier that tried to identify whether this was speaker A or B or something. All right. The advent of deep learning and deep supervised learning basically try to integrate these two boxes into one. So traditionally, you might feature engineer the yellow box and then learn a very simple, say, a k-means classifier on top of that. But deep learning tries to integrate this into one big pipeline and learn this end to end. And the way that works is basically having a lot of examples of your output, say the speaker or clean speech or whatever thing it is that you're trying to predict, and having that coupled with the same instance in, say, a noisy setting or the audio waveform that you have as your input. And then you try to learn these two boxes jointly. In these deep supervised settings, you'll basically have this representation as an implicit hierarchical thing as you go down the depth of a neural network. And typically you think of it as having initially some very low-level features. In images, it's like edges and stuff like that. And on the right-hand side of the non-explicit representation, you would have more, you have combined these edges into notions of, say, an ear of a dog or something like that. And in audio, these things map to similar stuff. It's like frequencies, phonemes, words, then speakers in this hierarchy of things, depending on what you're trying to apply it to. But the tack that we're trying to take today instead with this work is trying to say, well, maybe we should go about learning systems in an unsupervised way, or learning representations without having this explicit end-to-end supervised learning setup. And a way to do that, there are many, but the way we'll do it today is talking about autoencoders. And autoencoders have three central tenets to them. The first is that compression is comprehension. So this is a very old informational theory adage that if you have compressed a signal, produced, say, fewer bits or a transcript of an audio input signal, then you have somehow comprehended it. That is, if, say, the transcript is accurate. So here we have an audio waveform going into an encoder or compressor, not a hearing aid compressor, but a computer science compressor, and it produces the transcript. So if you've compressed it well, you've maybe also comprehended it. And an autoencoder then tries to learn this compression through coupling it with a reconstruction such that a construction can guide compression. And in this case, input the input waveform, you encode it, get a transcript or a representation. It doesn't have to be a transcript at all. It's just for ease of representation here. And then you couple learning the encoder with a decoder or a deconstructor or reconstructor that then reconstructs the original input waveform. And by trying to minimize the distance between these two waveforms, the input and the output, you can learn both to encode and decode or compress. And if you have a really good performance, you can be said to have done good compression and hence good comprehension. You can do this arbitrarily well. If you basically just have a identity function for the green and the blue, you get a minimal distance between these two things and you've learned nothing because you've not compressed anything. So a central thing to autoencoders is the bottleneck that you're basically imposing. This example is a textual representation, which is a very heavy compression in terms of the amount of bits. You might be very familiar with other types of compression. It could be temporal, lower temporal resolution. It could be other notions of what a bottleneck might be. But another thing central to making autoencoders work is posing them as probabilistic models or getting variational autoencoders. And here the last thing to then know is that if we're trying to reconstruct with an autoencoder, being very certain can fool this construction and hence the learning. So what we might do to improve an autoencoder is to impose or endow the model with the capabilities of parameterizing distributions. So the example here being that the model can say that it's a little bit unsure whether that word was supposed to be cat or hat. And so it can try to decode both. And it might see that hat fits better with the original input waveform. So this produces a longer learning signal or stronger learning signal. And it also gives us some information that we can use when we then try to use this model out in the real world. And I'll get back to both of these aspects of it. So when you do variational autoencoders, you can basically learn a representation. And it's not as explicit as a transcript, the representations we're learning. It's basically vectors or time series of very high dimensional stuff going on. So it's not directly interpretable, but they should still be useful. And hopefully we can get them to transfer to a task that we're interested in, or couple the learning of the representation with a supervised learning setup. And I'll also get back to what I mean by that in just a second. All right. So this concept of a variational autoencoder is something that we can then use to improve speaker separation. And the formalism that we get from the theory of VAEs, variational autoencoders, is something we can try to understand maybe why we see these issues with generalization that we've also talked a little bit about. So all of the others have already talked about why we should want to do this, but on a global scale, about 5% of the population have troubles with hearing loss. And another central problem for a hearing aid manufacturer is at least that if you could have benefited maybe from a hearing aid, only about 1 in 2, even in Denmark with a high adoption rate, choose to use a hearing aid. So there's something of a gap between what the hearing aid can provide and what we need to do. And untreated hearing loss has societally and in terms of quality of life for the individual, huge issues. On a global scale, annually, we spend about 3 times the GDP of Denmark in untreated hearing care or untreated hearing loss direct costs. So societally, it's a problem that we sort of need to fix. And if we ask hearing aid users what it is that they need, about 94.8% of them, or almost all, say that they want to improve speech in noise, which is what we've been talking about today. How can we improve, in particular, communicating or doing speaker separation potentially in a noisy situation? And speaker separation is something that can help us in these scenarios, and in particular, deep learning setups for this have been tremendously powerful in doing this. So I'll try to go through a very archetypal model for this called these time domain audio separation networks, or for short TASNets. And they look like this. The left-hand side, X, is an input of a mixture. We've talked about this a little bit. It might look like this. This is 50-ish milliseconds of audio at, say, I think it's 16 kilohertz. And it goes into the blue box, or the encoder, or the compressor, producing a set latent representation. Here it's a deterministic thing, producing this image. So it's blowing up the one-dimensional monaural signal into a 512 channels on the y-axis, but it's decreasing the temporal resolution. This encoding then goes into a masker or separator, which produces masks, so a mask A and a mask B. So by looking at this encoding, the separator is trying to say, well, which parts of this representation should I filter out in entirely the same way as the existing spectrogram-based approaches that Lars talked about. If you then apply these masks element-wise, you produce estimates of the single sources. And if you know the true sources, you can do backpropagation and actually learn these in a supervised fashion. So this works beautifully. And then that is basically a deep supervised speaker separation setup. But it has a wealth of issues. One of them being that you basically need very good quality and large data sets. And if you don't, it tends to not train or generalize poorly. I have some figures later on that sort of highlights this. When you do have a large data set, it works really well. But if you then try to take it out of a very controlled setting, say you know the speaker, or you know the noise, or you know the spatial configuration of things, or you know the hardware, or it's the same mic, all of these things, when you try to change them slightly and go out into the real world, you tend to basically fall flat on their faces, these models. And we try to solve this by doing three different things. We're using this autoencoder or bow tie formalism around it. Especially, we know that we can improve autoencoders with probabilistic approaches. And I'll get back to this bugle in just a second. So the autoencoder, if you squint a little bit, you can see that these TASNets resemble an autoencoder. At least we have both a compression-ish thing, the blue one, and a decompression or reconstruction setup. And then we have some extra thing going on that modifies things. We know that we can improve the autoencoders by introducing the probabilistic formalism. So maybe we can do the same with these TASNets. And this amounts to introducing some stochasticity during modeling. So very simplistically, instead of producing a single number for each learned component in the encoding, we're basically, say, producing 6 different numbers and putting them on the face of a die, rolling that die, and then propagating only the outcome of that one. And why is it cool then? And what can we use this for? Well, from the formalism of variational autoencoders, we get rate distortion theory. And this type of theory can basically help us try to understand why sometimes these models are likely to not generalize, or at least aspects of it. So the first axis measures distortion. How much are we changing our signal? If we have a large distortion from our left-hand side input to the output in an autoencoder, we're introducing a large distortion. In our case, we're interpreting this distortion as a single speaker estimation from the mixture. So it's not classic distortion, but distortion of our estimate of the single speaker. And the rate here is then something that has to do with this stochasticity. And you can think of it as how much information am I sending through? So in classic communication technology, this might be something like bits per second. But in our scenario, we're talking more about it as a measurement of how deterministic things are, or how entropic are our distributions. So for a die, this might be, if you have the same number on all the faces of the die, it's a very deterministic thing, and the rate is very high. Whereas if you have different numbers on all of them, you have a low rate. And in the lab, these models work by basically getting curves that look like this. You can improve your distortions arbitrarily well and get very good estimates, so lower is better for the distortion, by sending more and more information through. But in the lab, this works really well, but if you take it out into the real world, there's sort of an inflection point where the information that you're sending through is no longer informative of your distortion task, it's actually destructive of it. And this, you could argue, is basically just overfitting, but the thing that's different here is that we are actually quantifying this term, the rate term, during training and minimizing it when we do it in this variational inference setup. Whereas existing models that do classic supervised learning are only just trying to optimize this distortion. So even though we see really high performing deep learning models do really, really well in producing good distortions, the issue is that, The issue is that they might do so at the cost of basically just sending more and more information through, and that's likely to generalize poorly. We can also visualize these as these red arrows that if you are at the top end here, you have in the lab really good performance, but you get a large generalization gap, and that's what we're trying to minimize. And that's where this bugle comes in. We want to find something that's at the middle of the bugle, not the mouthpiece, or either ends of the bugles, basically. We want a good trade-off between the two. All right, so now I just want to talk a little bit about the more specific results of this. So just to make something very clear, the differences to what the two previous speakers have been talking about, they've been talking about spectral approaches to doing speaker separation. What I'm talking about are time domain approaches. And in terms of computational complexities, these are quite different. We're modeling the raw audio is computationally a much larger thing in terms of the raw amount of compute that you need. And as Lars talked about, this is of course important when you're talking about hearing aids. So this is sort of a caveat to what we're talking about. This is visualized here as, you have thousands of samples per second, obviously. These are basically an overview of the setup that Lars talked about, with having a time frequency representation, masking that with a deep neural network, filtering then, and then inverting that. And the cool thing here is that these models that I'm talking about right now resemble them in many ways, except for the fact that we have a more flexible encoder and decoder. So instead of focusing on a classic STFT or something similar to that, we're allowing the model to be flexible at what it decides to represent in its representation and how it chooses to then separate in that representation. So this is a figure from the original computationally paper by Liu and Miskarani. And I don't want to go into details of the architecture, but what I do want to show you is that when you train these models with a very simple linear one convolution encoder, you get actually encoders that resemble a filter bank. And these filter banks have learned to represent the mixture waveform in a way that allows it to separate. So in this case, if you're looking at the lower hand side of these basis indices, it's learned a filter bank where it has an over complete representation of a given frequency because it needs to be phase sensitive in order to actually separate speakers that might have overlapping frequency content. And this is fed into the masker that keeps track of these long-term dependencies, but it basically does really well. And the encoder here is quite simple, but it does away with some assumptions that actually hurt performance. So this original computational paper showed how using these convolutional testnets in a controlled setting actually improves beyond the ideal ratio mask that Lars talked a little bit about. In terms of the perceptual performance, users would prefer generally the testnet outputs to the ideal ratio masks. And the problem here is that, of course, the IRMs are fixed to this encoder decoder and not an imperfect inversion of the decoder, essentially. Right, so the generalizations issues that I talked about, and we talked a little about data previously too, can be shown like this. So imagine you have a model that's trained on 100 hours of speech from a particular data set called LibRemix. When you evaluate that on the test set from LibRemix, you get a distortion, or this is the opposite of a distortion, so a scale invariant signal distortion ratio improvement, so higher is better. You get an 11 dB of performance on the test set. So that's just like, that's where we start with this particular model. If you try to take it out into a new data set, sort of mimicking the real world, which is new speakers, although same noise here, you see a drop of about 2 dB. This is something you can alleviate by increasing the data set size by 3 times or something like that. It becomes a little bit less the drop is still there. But it's also the case that if you have a smaller data set, which is the case of the blue one, wham, you see a tremendous drop in going from its training domain, or the domain it's familiar with, to a new domain. So now comes a few slides about variational autoencoders that I'll decide not to go through in order to also show you some results, but we can get back to them if you're interested. What I want to show you is if you take a testnet and then produce distributions over the encodings and the masks and the decoded single sources, you get a variational testnet that can actually now be interpreted in terms of rate distortions. And that gives you a model that also optimizes the rate or the amount of information that it's sending through. And that results in simple generalization increases. So this is a pretty dense matrix, and I just want to highlight one thing. So we train different models a testnet, a deterministic testnet, or a rational inference testnet in a noisy condition on LibriMix. So it's always noisy and it's always trained on LibriMix. And when you train a variation version of the testnet, you actually see these small but consistent improvement across all conditions, both noisy and clean, different architectures of the separator. So a later improved version of the separator than the one in the original testnet. And we see that it also improves in new domains. So generalization is just generally, on this metric at least, improved, and the drop of the generalization gap, or the red arrow of the bugle, is also decreased. But beyond that, we can try to understand this rate distortion trade-off that I talked about. So if we look at a curve that's more familiar to some people, maybe where the rate is on the first axis and the distortion is on the left-hand side axis, we can see that focusing on a low noise condition, for instance, that the rate, if you send no information through, you cannot do speaker separation. So there's no information in the latent space or your representation to do the separation. But as you increase the rate, you see better and better separation. At some point, you hit an optimal point with the star, and as you send more information, you basically degrade your performance in a new domain. And this is consistent across low, medium, high noise cases. It's consistent for real speech on LibriMix to VSTK, so generalization to new data sets. And a slightly more complicated setup that is super cool about these models is that you can actually do unsupervised code training. So a central issue with supervised learning is that you need these data sets. So in order to train these three model components, the encoder, the masker, and the decoder, you need examples of X and S and SA and SB, so these single sources. But we don't have a lot of that. So in comparison to, say, all of the audio of YouTube, we don't have a lot of estimated single sources. And typically when we construct these data sets, we also imposing sort of weird assumptions about how they work. They're anechoically mixed, or they're additively mixed, or there are no rooms, or a lot of weirdness about how we actually construct these tasks that we are learning. But these models, if you take them as variational autoencoders, you can basically skip the separation setup. So the separation of the masker, the green block here, is something we can decide to circumvent in cases. So we might decide to do the orange path instead and take a single source, encode it and decode it, and use that as a learning signal. This circumvents the green box and thus produce a stronger learning gradient for the encoder decoder step, producing generally more perceptually sensible approaches without the artifacts produced by the separation. But another cool thing is that you can encode the mixture directly into an encoding and decode that without separation too. So now you can learn when you have that signal from the single sources, but when you don't have that signal, which is much more abundant, you can learn from the mixture itself, producing much more realistic encoding decoding pairs for learning. Another thing that gives you, when you can also encode the mixture itself, is something called uncertainty quantification. So a central thing you'd be interested in when you use this, say in a hearing aid, is whether it works or not. So it's quite well known that deep learning algorithms tend to fall ungracefully. They basically just fall off a cliff when they don't work. So they have a tight area where they work really well and things look good or sound good. And then once you fall off that, it basically becomes gibberish. And you'd like to know whether what you're presenting to your hearing aid user or whoever is using your algorithm, whether that's the case right now or not. But you don't, because you need your single sources to actually estimate this error in a sense. So if you have this error, the distortion error on the single sources in a controlled setting where you know this, you would like to estimate this without knowledge of it in an unintrusive manner. And you could do this with the mixture autoencoding. So referring back to this unsupervised code training setup, instead of looking at the single sources, you basically look at how well you're representing the input X. So X set and back to the reconstruction here is something of a task that informs how well are we doing the representation of the signal. And if we're doing the representation good, we are also doing the distortion on the separation good or well. Meaning that as long as we have a good mixture autoencoding, we're also having good separation performance. And if we have a positive correlation here, we actually have a signal informing us whether or not we should maybe fall back to some of the more classic approaches that Mads also talked about that aren't deep learning based. Because deep learning works really well when it works, but when it doesn't, it's horrible. So this sort of signal is basically something that we can use to fall back or decide whether or not to use it. And it generalizes also to unseen conditions. So these uncertainty quantifications are actually somewhat calibrated, and we can definitely do more elaborate ways of interpreting this signal. All right, I don't want to go through all of this. So as a quick wrap up, what I've been trying to tell you here is that supervised learning approaches to deep speaker separation are very powerful, but they do have some limitations, especially when it comes to generalization. And representation learning, and in particular probabilistic approaches to it, have some super cool things that we can do. The rate distortion setup allows us to try to understand why existing models aren't generalizing, and it also provides us with a way of optimizing models to directly consider a rate, and so actually might generalize better. And when you do this unsupervised co-training setup, you also have a way of quantifying whether your model knows what it's doing or not, which is an overlooked but key selling point for these approaches, I'd say. Yes, that's it for me.
Thanks, Rasmus. Really good. Definitely a more like overview in general. So that was very, very comprehensive. Maybe you guys can come back and then we can take the Q&A. So Mats, you already went ahead and answered the questions, but maybe you can just talk a little bit about the, let's say, the top 3 questions that was asked, so that we also have it recorded in the webinar. So the most interesting things.
Yeah. Let me see here.
In the insert.
Yeah. So I was just going to look at which ones were the most interesting. So Giovanni asks, how do you choose what speakers are decided and what speakers are interferers? And I think that's a really good question in any source separation scenario. Of course, in something like a hearing aid, you have a better idea about what you're looking for. But I think actually that the approach I presented is really interesting in that respect, because you form clusters based on what is similar in terms of what is similar in terms of what you think is speech and what is similar in terms of noise. So in a broad sense, you get clusters observing the same acoustic phenomenon, or whatever you want to call it. And then very often that turns out to be a speaker. You can, in the codebook approach, and codebook sounds terribly dated, which I also pointed out to my students doing this work. But yeah, right, or maybe more even. But we can call it dictionary or whatever. But it's really just a model. And these models, you can of course also, as I mentioned, you can model specific speakers. You can model specific noises in the noise code books and all that, and that will help you form the clusters and define what you're going to extract. I know that's a bit of a vague answer, but I think that's actually why this approach is interesting, right? That you start with these pre-trained models that you then have in each microphone that enable all this other stuff, forming the subnetworks and actually enhancing individual speakers. Yeah,
like literally separating.
Yeah,
in the physical sense somehow.
Yeah. Let's see here. Any other questions here that? I posted to those interested. I posted links in the Q&A to the papers. Otherwise, you can go to Aalborg University's VPN page and find the papers there. If anybody's interested in code, people can write me and I'll share what I'm able to share. Yeah.
Cool. We can also share those links later so people have access to everything afterwards. All right. That's good. So let's just take the question that I hear. So Giovanni Bologna asks, is the variational task net much slower to train than the deterministic task net? I guess that's for you, Rasmus.
Yeah, that's a brilliant question. So in terms of inference costs, or whatever you want to call it, modernly, when you apply the model, it's insignificant, the extra things you need to do the probabilistic stuff. But when you're training, it roughly doubles the training time, particularly in getting those last improvements in the very last cases. So the last 1 or 2 dBs where the stochasticity during training actually enables you to improve in a sense over the deterministic case. So certainly it does improve or increase the training time a little bit. Yeah, but not greatly, I'd say.
Okay. Cool. So the next question for you as well is, have you identified any common causes of the trained model to fall off the cliff? Are there any indicators of better or worse differences between test and training set? Asked Jens Lindell.
Aside from people throwing GPUs over cliffs, few are that. So the obvious thing is that the model has a too high rate, which is what we see when we quantify the rate in the variational inference setup. But when you have very collapsed distributions on top, like a deterministic output, you get that. But that's a low level difference between models. In terms of data sets, what I see, and I'm sure Lars and Les can add more to that, is all of these various aspects that I talked about, like different characteristics of the noise. Is it stationary? Is it not? Is it from cafes, or is it from European cafes? Or is the mic hardware different? Is the speaker language different? Is the root language? I mean, all of those things that we know are now something that pops up because our scale at these deep learning systems are now so performant that these things become important, whereas before we had fit models to micro data sets, in a sense where this type of generalization wasn't expected. You weren't expected to train a model that included Mandarin to also work in Spanish or something like that, whereas the scale of these models now actually in a sense enable that. Yeah.
Cool. Do you guys have any comments to that? Or no, seems like not. Lars?
I have a question for you, Rasmus. What is the latency of your system?
That's a good question. So in terms of the rate distortion setup, you can think of the latency or the computational demands as an extra axis in terms of the achievable distortion. So we can have a causal system with, algorithm latency, but in terms of chunk sizes and processing that you're doing in audio anyway, it is trivial, or you can increase it and actually get the performance that you're seeing. These are very, the ones I presented here were for offline processing, basically, in a sense. It's non-causal. I think I don't want to put a number on it.
Okay, thanks.
All right, Rasmus, from Tanya, could you elaborate on your rate definition? How do you calculate it in your setting?
Sure. So it's a weird terminology. Some call it the prior divergency. So from variational Bayesian inference, it's the KL, the Kullback-Leibler divergence from the prior. So our distributions that we're parameterizing are, say, a Gaussian, and if we have a isotropic Gaussian prior, the KL divergence, sort of like Mads talked about with the IS divergence. This is just different divergence that measured in a slightly different way. It's basically just how dissimilar are two distributions, and that's what the rate is doing. So for Gaussians, it amounts to having very different means or mu's in the Gaussian, but modified by their variancy, variancy-dependent difference in means.
Cool. Matt?
Yeah. So just a note there for Gaussian time series, KL reduces to IS, so they're very closely related.
Yeah. So in our case, the maskless are log normal because we want these non-negative properties that are nice in terms of interpretation. But yeah, that's a good point.
All right, no one is unmuting the microphone, so I can also ask a question. But my brain is more like an acoustics brain, so I kind of have to take a few steps back here because you guys are very much into the details, and I'm not that guy. So what I'm thinking about is these libraries. I mean, because sound is there's just so many elements that can kind of blur the data, right? And you were talking about if you have more data, you had better results, or That's at least what I interpreted from what you said, Rasmus. But then I'm thinking about, like, okay, first of all, we have the fundamental, then we have the formants of the voice, and then we have men, women, and then we have consonants and vowels. And so there's just so much complexity in speech. How do you make sense of that, especially when you're taking care of the libraries? Like, is it just random? Is it like feed everything in there and see what happens? Because that's very dangerous as well, right? So, and languages as well. I mean, there's just so many things that we have to be careful about to figure out what we should focus on. What's the output we want? So, do you guys have some input on that?
I can say something about it that I didn't mention in the talk, because we looked at mixtures of male and male-female, and I didn't show you the results, but we actually found that separating two males is just as easy as, say, a male-female mixture, which is not what we expected, because usually, traditionally, it's being said that there is a difference in the fundamental frequency makes the job easier. Apparently, that's not the case. So, and then we tried to see what kind of features the network is exploiting, but we didn't come up with a very clear answer. It's mostly this simply the glimpsing opportunity, the way I see it.
Yes.
Can I add a comment there?
Go.
Yeah, there was. So if you look back before the DNN stuff came along to how people were going about source separation, a lot of it was spectral modeling, NMF, and those types of techniques. And it was interesting that very few, if any of those, actually made use of pitch cues. Now that Lars mentioned pitch, because we know from auditory scene analysis and computational auditory scene analysis that it's presumably an important cue. But there was actually a paper at ICASP this year where they were trying to find out what some deep learning methods, what features they were actually sensitive to. So they would perturb properties of the signals. For example, ruining pitch structure and doing other kinds of things. And they actually found that the deep learning methods were implicitly learning cues such as pitch. So if you messed with the pitch cues, performance actually degraded a lot. I thought that was very interesting, given how previous source separation methods have worked over the past few decades.
I think a thing within the community of say deep learning speaker separation or deep learning audio modeling generally is that there are the people who remember the history, and then there are the dumbasses that just try to learn without actually thinking about it. And I think we see the advent now of models that actually integrate the long history of domain knowledge within this in the ways that you talk about, Mads, too. Maybe a comment on your original question, Pedro, with how do you handle it? I think the deep learning approach to this is just to create a huge data set and create a sufficiently flexible model that can handle it. But then, as Lars points out, you get huge delays and that won't work. So you need to be smart about it. But from the modeling side of things, a way you can, I at least am interested in looking at it, is that you model explicitly hierarchies. So these variational autoencoders, for instance, you can learn hierarchical variational autoencoders that enable you to explicitly have a representation or learn representations where you think, there are frequency components, there are phonemes, there are words, and you need to match these temporal scales and cook them into your model. So that's sort of a domain knowledge that you put in, that you need these multi-scale representations, basically. And that allows you to explicitly look at these macro level stuff too, identities, languages, sentence structures too.
Right. Yeah, I'm also thinking about, like vowels have a completely different spectral information than consonants, right? And they're so different and so spread. So should we actually, in the input, kind of isolate those things and see, should we actually separate it to see if the results in there would be interesting or not? I don't know. But and also, like when you're talking, up and down, all kinds of stuff. So yeah, anyway, I think there's a lot to be said here and a lot to be discussed. So it's good that you guys know each other and get to talk more about this and do more interesting research. Any last comments, because we have to close soon?
Thank you.
Yeah,
thanks for organizing it too.
Thanks, Stu. It's been a pleasure. All of you, thanks a lot for coming. I just want to say one last comment that when people log out, there will be a survey. So we need your input so that we can make these webinars better and better. And yeah, the presentation will be uploaded, both the presentations and the webinar, and people can always come back to this and learn it again. So thanks a lot, guys, for coming today, and see you soon.
Bye-bye. Pleasure.
All right. Pleasure. See you.